Over the past 7 years, we've put a great emphasis on the development of structural fire design modules for AxisVM. In 2018, with the AxisVM X4, we released the module SD8 for fire design of steel structures. In 2019, with AxisVM X5, we introduced the module TD8 for fire design of timber structures. In 2022, we made our first step in concrete fire design in the form of RC8B module released in X6, which made structural fire design of concrete columns and beams possible. And with RC8S released in the current AxisVM X7 version, we are making structural fire design possible for concrete slabs and walls possible. With these modules, we are offering a complete solution when it comes to structural fire design for a whole variety of structures. Fire effect is a relatively rare extreme effect. Its extreme nature is reflected in its often extremely severe consequences and its highly nonlinear nature and structural response. The key to ensure the proper level of reliability against fire is the structural fire design. Reliability criteria, definition of fire actions, combination rules can be found in the corresponding Eurocode standards. Requirements related to different kinds of elements may be found in national regulations, such as insulation, integrity, and load-bearing capacity. Like wind and earthquake, fire can impose large demands on structures with the same potential for extensive structural damage and collapse. However, the difference is that in the current state of practice, structures are engineered for wind and earthquake loads by structural engineers. In contrast, the majority of structures are not engineered for fire, and indeed most structural engineers have limited education on how structures behave under fire loading. The modeling of fire effects in AxisVM is based on fire curves. RC8S and all fire design modules of the software SD8, TD8 and RC8B uses fire curves to describe the fire effect. This is the most often used approach to describe the effect of fire, which is essentially a function describing the gas temperature as a function of time. It contains significant approximations, so for example by assuming the same temperature at all points in the room. All structural fire design modules in AxisVM follow the prescriptive design rules by using fire curves and simplified calculation models. It is also important to note that member analysis can be performed in AxisVM. It means that the fire safety is verified on isolated members. To summarize, RC8S offers a tool for fire design of concrete surfaces according to Eurocode 2, the Swiss SIA 262, and the Dutch NTC standards. It uses standard and custom fire curves for fire design parameters, and based on the fire design parameters, it can analyze the temperature distribution inside the cross-section. Design takes into account the temperature of the longitudinal reinforcement as well as the spalling of the damaged concrete layers. The end result is the required amount of reinforcement in the concrete surface under fire situation and the verification of the actual applied reinforcements. In the following demonstration, the workflow of all structural fire design modules will be presented, including the new RC8S module and showing the RC8B, SD8 and TD8 modules as well. The structure which is being used is a multi-story residential building. As the color coding shows, it is built up from concrete walls and floors, having a steel structure mixed with timber on the roof. Element type-wise, steel and timber members uses the 6 degree of freedom beam element, bracings uses the 1D truss element type, wall and floor domains are defined as shell elements, and members in the plane of the floor are defined as a rib type of element. Moving on to the load step, the model is already prepped up with basic load groups and load cases like permanent load group for self-weight type of loadings, variable load groups for the live loads of different usage scenarios, and there are annex-based, automatically generated meteorological loadings for wind, snow, and exceptional snow load groups. What is yet missing is the fire load group and fire load cases. In order to perform structural fire design in AxisVM, we need to add these to the model. This is performed through the load groups and load cases dialog. We create one fire load group and add fire load cases for each story of the structure this time. We are also setting them as mutually exclusive load cases, meaning that in a critical load combination, only one load case from the load group will be taken into account at a time. When a fire load case is active under the Loads tab, which is the case right now, there are only two buttons active on the user interface: the Define Fire Effect on line elements and the Define Fire Effect on domains buttons. First, Fire Effect on steel members will be added on the rooftop. During the course of the definition of fire load parameters, we need to define the fire curve, from which the ISO, the external, the hydrocarbon, the parametric, and the user-defined curves are available. We also need to set the requirements in minutes. 30 minutes or higher requirement can only be satisfied using fire protection. Steel temperatures above 550 to 600 degrees of Celsius are too high. 90% of problems with high utilization ratio are coming from this issue. The standard conforming steel temperature is calculated automatically and represented with black curve on the fire curve. We can set the exposition of the member, which influences the value of shadow correction factor and the section factor. We can choose to add fire protection. In this case, we need to define the physical properties of the protection itself. We can automatically calculate the shadow effect and section factor for eye, box, pipe, and angle cross sections. And finally, we can also calculate the temperature distribution inside the cross-section. Temperatures within the cross-section are calculated by finite difference method, with which a two-dimensional heat conduction problem is being solved. As it was mentioned during the presentation, AxisVM fire design process is based on isolated member approach. For this, we need to know internal forces, boundary conditions, material, cross-section, and steel temperatures. The steel material itself is a good heat conductor and heats up very quickly in a fire. The strength and stiffness parameters of the material decreases rapidly on elevated temperatures, which makes steel structures very sensitive to strength and especially to stability failures in a fire. So after we have the steel temperature, we can reduce the yield strength and obtain new buckling reduction factors according to the lower stiffness and modified boundary conditions. Next, we will define the fire effect on timber elements. The process is the same, but there are less parameters to define. Again, fire curves needs to be selected. ISO and parametric curves are available. Time requirement has to be set. Exposure of the cross-section against the fire needs to be selected, and optionally fire protection can be added. For member analysis on isolated members for timber elements, we need to know internal forces, boundary conditions, material, cross-section, and the charring depth. According to the design codes, reduced cross-section method is implemented in the software, where the design calculations are performed on a cross-section with reduced dimensions. Continuing with the definition of fire effect on concrete elements, in fire load case story 4. First, showing the process for a concrete column. Again, fire curves will need to be selected. ISO, external, hydrocarbon, and parametric curves are available. Time requirement has to be set, and exposure of the cross-section against fire needs to be selected. Based on these parameters, the temperature distribution within the cross-section can be obtained by clicking on the Analysis button. And lastly, fire effect will be defined on the domain of story 4 using the new define fire effect on domain function. This will work exactly the same as in the case of concrete line element showed before, but the cross-section, of course, is now a segment of the slab. For member analysis on isolated members for concrete elements, we need to know the internal forces, boundary conditions, material cross-section, reinforcement, and the distribution of temperatures within the cross-section. The so-called 500 degrees of Celsius isotherm method simplified calculation model is implemented in AxisVM, where the damaged concrete with temperature exceeding 500 degrees of Celsius is assumed not to contribute to the load-bearing capacity of the member, whilst the residual concrete cross-section retains its initial values of strength and modulus of elasticity. The strength and stiffness parameters of steel material of the rebars are considered according to the temperature of each rebar separately. Jumping a little bit to the point where all elements of each story has fire effect assigned to them with the technique just shown. An important side note is that in AxisVM, in most cases we do not recommend to generate or create manual load combinations, as critical results envelope diagrams are superposed from load cases on the fly after the analysis. However, if for any reason manual load combinations are created containing fire load cases, it is crucial to set the type of the combination to ultimate limit state accidental, otherwise fire design will not be performed on this combination. Moving on to the analysis, it is important to note that fire effect will not affect the analysis results only if we checked in during the definition of fire effects to apply fire effects as thermal load. In case of statically indeterminate structures, consideration of kinematic loads such as the thermal load itself is usually not necessary, therefore is being neglected in this example now. So as you can see, since fire effects were not acting as thermal loads, there are no internal forces for these load cases after the analysis in this case. Continuing with the design, let's see how RC8S module is used to deliver fire design results for concrete slabs. When defining basic reinforcement parameters for a slab, in order to perform the fire design for that particular slab as well, on the reinforcement parameters dialog we need to check the checkbox for fire design. After this, the software will be able to determine the required amount of reinforcements for the slab. By checking the critical results from ultimate limit state combinations using the minimum-maximum function, we can see that the required reinforcement, for example, in x direction bottom position is 689 square millimeter on a meter. Comparing this by checking critical results from ultimate limit state accidental combinations using the min-max values, we can see an increased amount of 757 square millimeters per meter reinforcement requirement. Checking the combination itself from which this result is obtained from, we can see that story 4 fire load case is included. Next, we will check the fire design of a concrete line element, a column in this example, using the RC8B module. To perform fire design on a concrete column, the column reinforcement function has to be started, where between the design parameters, fire resistance design has to be checked in. Reinforcement has to be added to the cross-section of the column, after which we switch to the column check tab, where design is being performed. Detailed calculation report is available for concrete column design. Checks are performed in a way that they are taking into consideration of the spalling and the damaged concrete layers, which neglected layers are shown graphically as well. Temperature of each rebar in the cross-section is also calculated and listed in table form, where the reduced yield strength and elastic modulus is listed for each of them. In case of fire design for steel members, using the SD8 module, the fire design option has to be turned on in the design parameters dialog. When design parameters has been assigned to members, design calculations are being performed. Clicking on a member, we can open up detailed design calculation report as well, where we can check the critical temperature calculated for that specific member for each performed check in the critical cross-section. Critical temperatures can vary along the member, which variation can be visualized as well. As for the fire design of timber elements using the TD8 module, the process is pretty much the same like in the case of steel members. The fire design has to be turned on in the design parameters dialog, which parameters are being assigned to the members. After that, the software performs the corresponding checks based on these parameters. The difference is that in case of timber elements, the software calculates the charring depth, with which it reduces the cross-section area on which the standard checks are being performed.